Dear students, so today we will talk about entropy, types of entropy basically. So entropy, entropy bound Ts here. S is entropy, T is temperature. So this is called bound energy. Bound energy available. So this entropy, we have two different types of entropies. One is thermal entropy, another is configurational entropy. Thermal entropy and configurational entropy. So this thermal energy depends on temperature, temperature dependent, and this configurational entropy does not depend upon that temperature, temperature independent. This configurational entropy, uh, it depend on configuration of configuration of atom. This configuration entropy depend upon the configuration of entropy and does not depend upon the temperature. So this thermal entropy is equal to kT. Thermal entropy is equal to kT. And here we know that bound energy is equal to temperature into entropy. Temperature Ts, temperature into entropy. And if we talk about that free energy, so this free energy is equal to uh, H. You know what is H? H is enthalpy, and this free energy is denoted by G. This this H is enthalpy. So we can write free energy, or G is equal to H minus Ts, or in words we can write free energy is equal to enthalpy minus bound energy. Enthalpy minus bound energy. Free energy is equal to enthalpy minus bound energy, or G is equal to H minus Ts. So we have three different types of that free energy. So now we will talk about that different types of free energies available. So these we also know that bound energy is also known as, this bound energy is also known as entropy factor. This is bound energy, or this one. This is entropy factor. Entropy factor. So first is that Gibbs free energy. Gibbs free energy. Then Helmholtz free energy. And the last one is thermodynamic free energy. Thermodynamic free energy. So what is thermodynamic free energy? Thermodynamic free energy. The energy in a physical system that can be converted into work in particular. So what is that thermodynamic free energy? The energy in a physical system, like we have some physical system, and this physical system is having some energy which can be converted into work in particular. This energy which is into this physical system, this can be converted into work in particular. This type of free energy is called thermodynamic free energy. Thermodynamic free energy. Now we shall talk about that Helmholtz free energy. Helmholtz free energy. The energy in a physical system that can be converted into work at a constant temperature and volume. At a constant temperature and volume, this is called Helmholtz free energy. Similar type of physical system, if we have a similar type of physical system, and now the energy is energy can be converted into work at a constant temperature and volume. This type of free energy is called Helmholtz free energy. Similarly, what is Gibbs free energy? This is the last one. Gibbs free energy. The total thing is similar, but now the work that energy can be converted into work at constant temperature and pressure. For Helmholtz, it was at constant temperature and volume, and for Gibbs free energy, it is at constant temperature and pressure. So these are the three different types of free energies. First is thermodynamic free energy. Second one is Helmholtz free energy, and the third one is Gibbs free energy. And we have just now we have discussed about that definition of these three free energies. So this Gibbs free energy, this is denoted by, this Gibbs free energy is denoted by G. Gibbs free energy is denoted by G, and this is equal to H minus Ts. Helmholtz free energy is denoted by E, capital E, and this is equal to U minus Ts. U is internal energy. You all know about this U, internal energy, and this is gives this is enthalpy. So Helmholtz free energy is U minus Ts, and Gibbs free energy is H minus Ts. Now for solid For solid, we know that H is equal to U plus PV, and PV is negligible for solid, and we can say that H is equal to U. For solid, H is equal to U, as PV is negligible, H is equal to U. So this H and U, these are equal for solids. So we can say for solids, Helmholtz free energy is equal to Gibbs free energy. G is equal to E in solids. G is equal to E. G is equal to E in solids. As for solid, PV is negligible and H is equal to U. So this H is equal to U. So we can write that G is equal to E, or Helmholtz free energy is equal to Gibbs free energy in case of solids. Now we shall talk about next topic. Our next topic, which is stability criteria. So I have already told you that stability criteria does not depend upon internal energy and that enthalpy. And at that time, I also told you that this stability criteria of a matter is depend upon free energy. Now I will show you how that stability criteria is depend on free energy. This side temperature, and this side free energy. This is the melting temperature or melting point. This is liquid. The blue line is for liquid. And the red line is for solid. Here the slope is 0. Here the slope is 0. So you can see this is the melting point. So before melting point, the liquid has more free energy than solid. Before melting point, liquid has more free energy than solid, and after that melting point, solid has more free energy than liquid. So from here we can say the state in which the free energy is minimum, that state will remain that in equilibrium at that condition. So like before melting point, as the free energy of solid is less than the free energy of liquid, that's why solid is solid is in equilibrium before melting point, and after melting point solid is having more free energy than the liquid. That's why as the liquid has less free energy after that melting point, so the liquid state is in equilibrium after that melting point. So from this graph we can easily say that which state is having that minimum amount of free energy, that state will be in equilibrium. And as that before melting point or melting temperature, the solid state is having less amount of free energy, so solid state is in equilibrium. And after that melting point, that liquid state is in equilibrium, as it is having less amount of that free energy. So the state of a matter depends on free energy. And we can say from here, we can say that the state in which the free energy is minimum, that state will be in equilibrium at that condition. So thus that stability criteria depends on that depends on free energy, not on internal energy, and on that or that on enthalpy. Now if we take an ice cube in room temperature, it started to melt itself without without applying any heat on it, or supplying any heat on it, or pressure, or any other the other thing. It started melting itself. Such process is called spontaneous process. In spontaneous process, change in free energy must be negative. In spontaneous process, that change in free energy must be negative. So change in it gives free energy. Delta G is equal to G final minus G initial. G final minus G initial. And now for spontaneous process, the del G will less than 0. Now if that del G is less than 0, then this process, we can call this process is a spontaneous process. This process is called spontaneous process. Our next topic is crystal geometry. Crystal geometry. So in crystal geometry, we have to learn about three different topics. These are space lattices, Number 2, crystal structure. And number 3, crystal directions and planes. So our first topic is space lattice. So now we will learn about space lattice. So what is space lattice? An infinite array of points in a 3D space such that every point has identical surrounding. So what is that space lattice? Let us say this point, and it is in a infinite array of points. Infinite array of points. Let us say this side it is infinite, this side infinite, this side infinite, and this side is also infinite. So here infinite array of point, and we are taking one single point. And this is obviously this should be a 3D space. So this point is surrounded by some identical points. This point is also like this one. This point is also surrounded by same identical points. So this is called space lattice, where an infinite area of points in 3D space such that every point has identical surroundings. Now, now if I take this point and move upward direction, this is A. Similarly, if I take this point and in the same direction with same amplitude, if I move, then I will get another identical point. This is also A. Like this, if I move like in this manner, in this direction and in this direction with same amplitude, so we will get same vector or same identical point. These are B. If we go like this, then also, or these are same. Let us say this is C. Then If I take like this point to this point to this point, so here also we will get a same identical point, and similarly in same direction with same amplitude, if we move upward like this, here also we can find a identical point like the initial one. Let us say these are D. So these AA, BB, CC and DD all are all are having identical surrounding. Now, if I take this is as X and this one is as Y. So this XY is coplanar. This XY is coplanar, but non-collinear. Non-collinear. How it can be linear? Like if we move this, and then again this, and again this. So this is collinear. This is collinear. Now let us take one square like this. This is A, this is B, like this. So if we rotate it, if we rotate it, if we rotate it 90 degree at 90-degree angle, if we rotate it at 90-degree angle, so we can get a similar arrangement, but not like the previous one. As it is a square, so all these A, B and AB, all these are equal. So after this 90 degree, if we rotate again at 90-degree angle, again 90 degree, again 90 degree, then we can get the initial position. The initial position, like 360 rotation, after 360-degree rotation, we can get the identical shape. We can get identical shape 90 plus 90 plus 90 plus 90, total 360. After 360-degree rotation, we can get the similar shape or identical shape. So this is called rotational symmetry. This is called rotational symmetry. Now, if we take a parallelepiped like this, like this. So after 90-degree rotation, now parallelepiped is lying on this side. After 90-degree rotation, it will lie on this side. Again, after 90-degree rotation, it will lie on this side. Then after that, in this side, then again on this side. So in this manner, after 360 rotation, after 360-degree rotation, we can get a similar, or we can get the identical shape. So this is called rotational symmetry. Now let us say we are in this position and moving to this position, and that position also. So in these two cases, we will get a similar identical point. The direction of these two and amplitude of these two are different. Still, we are getting identical points. So this is called translation symmetry. Translation symmetry. The first one, the first one is the rotational symmetry, and now it is translation symmetry. So these two types of symmetry we can see here. This one is the rotational symmetry, this one or this one, where we can get the identical shape after 360 degree of rotation, and this is the translation symmetry.